flux, the amount, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. So if you want to find the EMF, just find the rate of change of magnetic flux linkage. Then in that process, that will be the answer. So in that case here, we are going now to work in this way. So we have gotten the magnetic flux. Then to get magnetic flux linkage, you need to multiply the number of turns. So N. And remember, in this question, we are working out the number of turns. So if we are working out the rate of change, there must be the aspect of time, guys. So which means that we are going to have the magnetic flux linkage, which is this value at the numerator, divided by time. But time, guys, I know most of the students will make a mistake here. The time you are going to use is not the periodic time. You are not going to use the periodic time. The magnetic flux linkage is changing from 0 to this maximum point. That's where the change of the magnetic flux is starting from 0 to the maximum. So the time you'll use for the rate of change is a quarter of a period, because the change of magnetic flux is happening from within a quarter of a period. The flux will change from 0 to the maximum. That's why there's induced EMF up to the maximum. Then it will start decreasing to 0. So always the time you are using for the change of magnetic flux linkage, guys, is going to be a quarter a period. That's why you can see I'm having the periodic time times 0.25, a quarter, because the change of magnetic flux is happening between 0 and this middle point. So a quarter of a period. And if you work it out, you are going to get the number of turns being equals to 402, because you are going to equate this value you have here to 3.2, the average magnitude of induced EMF that was given there. A quarter, because the change of magnetic flux occurs over a quarter of the period. I believe you are not going to forget that, guys. Let's look at the next point here. We are told that in 1821, Michael Faraday made what is observed to be the first electric motor. This is in 1981, guys. Okay, so that was the first believed to be electric motor, which was having a stiff wire. There is a magnet, and that stiff wire was dipped in mercury, so it could be able to rotate that, and in the process of rotating is going to cut the magnetic field. And basically that is why we are having that. So we were told that the wire made 10 complete revolutions in 8.3 seconds. So if it's making 10 revolutions in 8.3, one revolution will be what? Yeah, so 10 is equals to 8.3. One revolution will be what? That will be 8.3 divided by 10, which is going to translate to 0.83 seconds, and that is going to represent the periodic time of this particular revolution. But we know angular velocity, because we are calculating the angular velocity of the wire. We know angular velocity is given by omega 2 pi over t. So if you substitute that, you are going to get a 7.57 radians per second. That is exactly what you are going to do at that given